dark matter fractions of early type galaxies.
Yes. So, hello everybody. I'm Rhea-Silvia Remus, and I'm working as a postdoc in the group of Andreas Burkhardt, who's already here. And it's my first time here, so I hope you enjoy the work I'm doing. Mostly I will talk about total density slopes, actually, but they are connected to dark matter fractions. So, yeah, let's go. So already on Monday, Aaron Dutton told us a little bit very interesting about the connection between dark matter halos and the central interstellar parts and all these kind of things and what you can do with dark matter distributions. And one approach, does it like me? Yes, it likes me. So one approach to do it is to look at cosmological simulations. So, and because I haven't been here before, you probably haven't been introduced to the magneticum simulation yet. This is why I will do it now. So the magneticum simulations actually are a set of hydrodynamical simulations, and you can see that we cover a quite big range of box sizes. They are all baryonic. So you see this is a more than 2,000 megaparsec box size baryonic simulation, and that is currently the biggest one that is available and has been already used quite a lot for cosmological comparison studies. If you are interested in that, please go to the webpage of the magneticum stuff. However, as I'm working on galaxies, the one that is interesting for me is a small box, because that's where I have enough resolution to study actually galaxy evolution. So what's in? There's a lot of stuff in. What's probably most important is it's an SPH Gadget 3 version modified. It has stellar winds, it has an AGN, it has metal cooling and stellar enrichment. It has all these kind of things in. So we should say, according to what we know, this is the standard that the best we can do at the moment. So this is the box I'm working on, and you can see this is very nice. This is the whole box. You see there's the clusters here. The blue stuff are the cluster halos. You have also a lot of galaxies sitting around, and if you zoom in, you see that you get all kind of galaxies. You get early type galaxies, and you get something that is disk-like galaxies. And that's already where the mess starts. Because the first thing to do if you have a box like this is you say, yay, I get disks, because normally that wasn't so common a couple of years ago. However, it starts to make a problem. Because in the moment you have disks, you also start with the messy business of how do I distinguish between ellipticals and spirals. Of course, you can say I do it by hand and check every galaxy, which means I have more than 600 galaxies resolved in the simulations. If I want to do that at every redshift, I'm pretty busy, or I need a bachelor student. Now, you can't abuse them like this, so you better start finding a mechanism to do that properly. There's several ways to do that. And for the questions I want to address here, we use a fairly simple way, which means we accept that we throw away quite a lot of galaxies. So what do we do actually? Well, we take each galaxy, and we look at the epsilon parameter for each star, which means we turn the galaxy on the main axis, then we calculate Jz for the star, calculate what it should be, the angular momentum if it would be on a circular orbit, and then we make histograms. And you see if you have something like a disk, it should peak somewhere around 1. And if it's something like a spheroidal, it should peak somewhere here around 0. As I said, this doesn't work for all galaxies, because there's, for example, these galaxies with big bulges, etc. pp. You will lose them. As I'm mostly interested in ETGs, I can live with this, but if you want a more fairly discussion about this, you should look at these papers, because there we also derived more advanced ways to split up galaxies in different classes. This is to show you it works. So here you see the stellar mass. Here you see the half-mass radius calculated from the simulation. Here you see with this simple mechanism what is an LTG in blue, and you see what is an early type galaxy in red, and in black you see the results from gamma. And what you can see is we fairly nicely reproduce this split up that you can also see in the observations between the two different kind of galaxies. What you also see is all the black dots that don't have any color in neither of the two plots. That's are the galaxies that we throw away, which is about more than half at the moment. But I'm going to throw away even more. Because for this work, I'm interested first of all in ETGs only, so bye-bye this plot. And also, I want to make sure that I have enough resolution to really look at the detailed distribution of particles, which means bye-bye low mass galaxies. And that leaves me with about 100 early type galaxies that I can study. And this is what I'm going to show you now. However, if you have a cosmological baryonic simulation, you only run that once with your favorite AGN model and your favorite stellar model. If you want to compare to different AGN models, you have to find another way. It's too expensive to do that with different boxes. So one way to do that is to say, I do zoom simulations, resimulations of individual halos. And this has been done for a set like here. This are the galaxies from OSA et al. 2010 and 12, and Michaela Hirschman. These are actually always the same galaxies, just once. It was simulated just with standard SPH, no AGN and stellar wind. And the second time it was simulated with no AGN, but with a strong wind and including metals. So we have the OSA as a standard comparison without everything. We have the wind simulations to check what does this stellar wind really contribute to the galaxies we look at. And then we have the magneticum galaxies where everything is in. And the first thing you can see is feedback plays already a crucial role if you just look at the mass-size relation. Because what you can see here is you need the AGN feedback to drive them up on the observed relations. The stellar feedback is not enough. What you even see, it makes it even worse. You see, these are the same galaxies, just with a lot of stellar feedback, and they even go down in the radii because they make so many stars themselves that the few early type galaxies you get, because you see this is only 5 out of them who make an early type, these are so compact, they never lie on the mass-size relation. So really here, the AGN is what you need to bring them where they should be. And what you can also see is, this is already important. This is different redshifts. It's Z equals 0.5, 1, and 2. Here, for comparison, you have the data from Van der Wel in 2014. Blue, again, is magneticum. Red is the OSAs. You find no wind simulations because the wind simulations are no early types at this redshift. And you see that, although it's only a few, to get them where they should be, you already at Z equals 2 need this feedback. Otherwise, it doesn't work. All right. Enough about feedback, let's talk about dark matter. So what do we want to know? The question is, how does the interplay between the stellar component and the dark matter component really works? And for that, one interesting thing to look at is simply the density profiles. So here you see the stellar component. Here you see the dark matter component of an example galaxy. And in black, you see the total profile of our galaxy. And what you can see very nicely is that the total profile can be actually fit nice by a power law, by a simple single power law with a slope gamma. And if we now look at these slopes, we find that most of them are close to isothermal, which means they are close to gamma equals -2. But they can become as steep as slopes of -3. The most interesting part here is also, this is independent of the feedback we use. So here, you see this gamma total against time, redshift here, here's look back time, and you can see this is the feedback, the AGN feedback one with the histogram behind it. The red one is a zoom control run without anything. You can see they are offset, but the shape of the evolution trend is the same, independent of the feedback. So the feedback changes the position, but doesn't change the behavior. So what you can see here, at higher redshift, the slopes are much, much steeper. So where does this come from? Well, the answer to this is accretion. Here you see 2 example galaxies. This is the redshift, and this is gamma total. And this galaxy has a lot of merging, dry merging. So you can see here, there's a flyby, and then this gamma total goes up, because there's a lot of merging happening, dry merging that drives the slope towards -2, because violent relaxation very efficiently in this dry merger cases drives the whole density to behave like this. If at Z equals 0 you find something which has still a steep slope, and this is the steepest we have in the simulation, what you can see here is it's kind of starved. It doesn't have any dry mergers at the lower redshifts. And that means it can't grow towards -2. So the slope at Z equals 0 tells you quite efficiently something about the late accretion history. about the dry accretion history a galaxy has had. You can also see that if you look at the in situ fractions of these galaxies, which means the fraction of stars the galaxy made itself and not accreted. And you can see that the guys that have still a very steep slope actually have a very high in situ fraction, which means they made a lot of stars themselves. And the other ones that sit down here, they have had a lot of dry merging, a lot of accretion. So that is the main driver of the evolution in the recent past. Now, the question is, do observers see the same? And this is the observation. And this doesn't look too good, right? So when we saw that, we were like, okay, we get the same range at z equals 0, which is from dynamical modeling. This is COMA and the SLUG survey, which you can see here. And this looks very nice. But then you go to higher redshifts, where we say, okay, there's a strong decline in the gamma toad. And the observers tell you, well, it's flat, maybe even decreasing, but definitely flat. So does this mean all of our simulations are wrong, or is there something else to it? So they kindly provided me with their program. This is a strong lensing program that has been used in the works by Sonnenfeld and Alessandro Sonnenfeld and et al. In their work. And all you need to plug in is the total mass within an Einstein radius, the effective radius, which we take as the half mass radius. Then you need to know how big should the Einstein radius be. And there I just followed Sonnenfeld et al. 2013 and said, okay, approximately 1.5 times the effective radius is what is on average observed. And then you calculate the line of sight velocity dispersion within half of this effective radius. This is what the observers do. And then their program gives them slopes. So I did that for our galaxies. And these are the simulated values. And this is what I get if I use a program. And now that's fun, because you see, if it would work completely like we expect, they should lie around this line. However, you see, face on, you have another line of sight, face on or edge on. Face on, you end up here, which means for all the steep slopes, I get a very flat slope out of the observation program. And for the edge on version, it's kind of better, but you see, especially at the higher redshifts, which are the open symbols, we are in trouble. And that's what happens if I use the mock observations, in blue you see, for our simulations. And you see that we can now quite nicely reproduce the trend observed, because we get a very flat slope, while indeed the intrinsic values go down like this. So now this is a point where we as simulators are happy, yay, simulation is not completely wrong. The observers, however, are now trying to understand where this is actually coming from, and I can't tell you the reasons for this in detail, but yeah, I'm looking forward to what comes out of it. Density slopes are cool for several reasons. One is because you can get information about what was the recent accretion history, but also because you can compare it to other things. And one remarkable thing is you can correlate it with the dark matter fraction within the effective radius. And this is interesting because you see that you get a very tight correlation between these two parameters, depending on the feedback that you have in. So here you see the magneticum ones, and here you see the ones without feedback from AGNs. And you again see stellar feedback doesn't make a difference. But this is a very tight correlation. And the galaxies move along this correlation in time, so it doesn't even really matter at what time you observe it. So this gives us, it's my last slide, a chance to compare two observations and to say, okay, we want to find a constraint, an independent constraint on our simulated AGN feedback. And this is where you find the observation. And this is the line from magneticum with AGN, and this is the one without AGN. And now you can see fairly nicely, if you can measure this, and you know where you should sit, you get information on average, and you can find a way to find out more about your AGN feedback that needs to be implied. So if you want to know more about it, you have to ask me or read the papers. Here's a quick summary, and so I'm done.
Hi, a couple questions that are to some extent related to an earlier talk and also to things you didn't mention. So Aaron Dutton explained that he expects to have compression or expansion,
Yes.
depending on
Yes.
star formation and amount of stars.
Yes.
It looks like you're generally getting expansion, but
No,
because I noticed that you're getting very flat dark matter profiles, and also
No.
okay. So
Yeah.
let me ask the second question, then maybe you can answer them both together. So there's a series of papers that started with Sand, Ellis et al., and the way those are looking, what they're doing is they're looking at the CD, the central galaxy in big clusters. They're taking out the effect of the stars as well as they can, and deducing that there's quite a lot of dark matter dominance in the central regions. So some of your early type galaxies were in clusters. Have you compared to that data?
Yes, I mean, we don't have enough in clusters. There's actually just 5 clusters in this box, and this is not enough for statistics.
Well,
And
except
the
they
big
claimed
strip-
that their results were fairly general.
Yeah, but for me, I didn't check the real differences because you don't really see something. The scatter is very big, and with just 5 galaxies, well, 2 of them even are not really ellipticals because they have an extended gas ring. So in this old crude classification, I could only compare it with 3 of them. And so this I didn't do. What I did is there's this paper, Dutton and Co. where they actually use the radius and plot the dark matter fraction behavior, where you can see where they should be if it's adiabatically contracted and if it's not. And all galaxies, they populate the space that is shown with the distribution. They completely recover the shape that is proposed by them, and they cover the whole space. So some of them are adiabatically contracted, some are not. And right now we are working on understanding this, but so far I can tell you it's most likely really is connected to the way they accrete. So this again plays a crucial role, exactly like what Aaron said. So this is the mechanism we see happening live and in action in this simulation. Yes.
So I very much enjoyed your talk, and I was just wondering if you had any physical intuition for why AGN make the disk bigger, or sorry, make the size of the galaxy bigger.
Well, it's because what happens is overcooling. You probably have heard of that. So what happens if you don't have an AGN? The gas goes to the center, it cools incredibly there, and you get a very dense core that actually makes your half-mass radius smaller. So what the AGN does, it prevents that. So the stars are formed further outside, there's more accretion and less in situ fraction, and that's why they are bigger. So that's basically the reason for it and why you need it. This changes for the galaxies that are smaller. But as you could see, I threw them out because the radial profiles are not that nice anymore. I can't be sure, the statistical error when I make the fit becomes so large that I didn't use them yet because I had to refine the method. So for the galaxies we have here, which is above 5 times 10 to the 10 solar masses, you can say, okay, the AGN is the main driver for getting these relations right. It's the same for the fundamental plane and all these other things. So you can, there's a couple of papers from our team out on this, and you can see that this is really, the AGN is very crucial for all these kind of scaling relations, like M star, J star, and all these things.
So I'm sorry there's no more time for questions for this. We can hold them till discussion.
Just come afterwards.
Thank you.